Welcome to this presentation, which continues discussion of step paper 1 question 4, which is in the first part of the presentation we did the first part and proved these two things, and now we've got to do hence or otherwise find all the solutions of these two rather forbidding looking equations. Just before I go on, let me just show you these acknowledgements. Here is the home page for STEP, which produces these exams which are for universities admissions for some universities in the UK. A site called MicroRigs, which is a lot of resources especially that support this STEP, and the Khan Academy, which is essentially the inspiration for this kind of presentations. Let me go back. Before we go into this, I would like to build up a couple of results, just check you understand a couple of things. Supposing I know that tan of alpha is equal to some number, which let's say is 11 over 2, that's the number we're dealing with here. So I know one solution to this equation, but I'm interested in all the solutions of tan x equals 11 over 2. So I'll write it tan x equals 11 over 2. Well, it turns out that x is equal to alpha plus n pi, where n is some integer. Do a z like that. That is, n is minus 2. We dot 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 any number minus 2, minus 1, 0, 1, 2, any integer you like, add n pi. And the reason for that is if we draw I'll try here roughly to draw the graphs of tan, something like this. Try and draw the axis across like this. This is a very ugly freehand for tan. It looks a bit like this, where there's asymptotes here at pi over 2 and minus pi over 2. If I draw the y-axis, it's through that point there. It's the y-axis. It's a very sketchy picture of a tan graph. Maybe just change to a different color, try and make this a little clearer. But it means if I've got some point here, which is 11 over 2, which is of interest, so maybe that's 11 over 2. If I've got alpha here, and I know that tan of alpha is on the graph, tan of alpha is equal to 11 over 2, then the other solutions are over here and continuing here and here and so on at a distance of pi, because essentially tangent is a periodic function with period pi. So anytime you get a solution, you add pi to which you get another solution. And there's something similar to say about cosine. If I've got cosine of alpha, or cosine beta, let's say, not to confuse some other number, let's say 2 over root 5, it doesn't really matter what the number is, then what are the other solutions? Then turns out that 2n pi plus or minus beta are all the solutions. And you can see that by drawing a sketch as well. Can I draw a better sketch for cos than I did for tan? Something like this, and we've got the x-axis like that, and the y-axis, let me see, is going to be like this. So the y-axis is like that, going through the maximum point here, so cos of 0 is 1. And here we've got, if we happen to have found the solution for a given value that's of interest, say this is a value here, say of 2 over root 5, and we find a solution that's of interest, well, cos is a function which is mirror image of itself in the y-axis. So if beta is a solution, minus beta will be a solution, and then it's periodic in 2 pi for both those solutions, which is why I wrote down here plus or minus beta, and then 2n pi, where n is any integer, just as before, any integer. Or I could equally have said n is a member of z, where you do this fancy Z, where Z stands for the integers. So those are the first two things I wanted to build up. I'm afraid there's another one I want to build up before we actually solve the problem. So let's see if I can make a bit more space here. And that's to work out something about cosine to the minus 1. If I told you that cosine of, I'll use degrees here, 60, that would be cosine pi over 3, by the way, if it were in radians, is equal to a half. But that's not the only angle whose cosine is a half. Cosine of minus 60 is equal to a half. And so is, if I add 2 pi to these, cosine of 300 is equal to a half. And so is cosine of minus 300. I can put plus or minus there. I can add other angles as well. Cosine of 420 is a half, and plus or minus for that matter as well. So if I ask then what is cosine to the minus 1 of a half, perhaps I've got all these values. Perhaps I have plus or minus 60, plus or minus 300, plus or minus 420. And in a way that's so if cosine to the minus 1 of a half, or if it means all the angles whose cosine is half, then it would be all of that. But there's something a little bit special going on here. We want to use cosine to the minus 1x in this equation here, where we want to apply a tangent to it, or tangent to 3 times cosine to the minus 1 of x. And if we're going to do that, it means that cosine to the minus 1x has to be a number. And that means, in effect, it's got to be a function. And if it's going to be a function, it can't be this many valued thing. We have to, in effect, choose or follow a definition which produces only one answer for cosine to the minus 1. If we choose, following the standard definition, we'll choose the value cosine to the minus 1 of a half is equal to 60 degrees, because in the standard definition, cosine to the minus 1 produces values that are in the range between 0 and pi, somewhere in the range 0 to pi, from 0 up to pi. And that's going to be important in the way we solve the last part of this problem. Let me go ahead right away. We've spent enough time preambling. Let's get on and do it. First of all, notice that what we've already proven in the first part is that tan of 3 theta, where that's 3, and theta is cos to the minus 1, 2 over root 5, 3 of all of that is equal to the 11 over 2. Not pi over 2, sorry about that. Let's try again. 11 over 2. And what we're asked to find out are all the solutions of tan of 3 cos to the minus 1x is equal to 11 over 2. Right, so from what we've said over here, all the solutions, this must mean that 3 cos to the minus 1x has to be equal to 3 cos to the minus 1, 2 over root 5 plus n pi, where n is, according to this, any integer. So that takes you from, if you've got the tangent and you've got one answer, to find all the answers you add n pi. So n appears to be any integer. Now, in fact, it can't be any integer. Let me just show you that. Let me just divide by 3 here in this equation. It's cos to the minus 1, 2 over root 5 plus n over 3 pi. Now, cos to the minus 1x has to be between 0 and pi. It's a function. It has to have one value, and we've chosen the value, or we followed the standard definition to take the value between 0 and pi. So that means this value here, cos to the minus 1 of 2 over root 5, which is an angle, and I won't go into this, but it's an angle less than 60 degrees, less than pi over 3. That angle plus n pi over 3 has to be between 0 and pi. And that can only happen, I'm going to change color for emphasis here, that can only happen if n is equal to 0 or 1 or 2, not any of the other values. So it's only those three values. So I want to solve this problem, this equation for x, given that n is equal to 0, 1 or 2. To do that, I apply cosine to both sides. So cosine of cosine to the minus 1 of x is equal to the cosine of all of this. Cosine to the minus 1, 2 over root 5 plus n pi over 3. These equations are not for the faint-hearted. It's a bit messy, but it gets simpler. Cosine of cosine to the minus 1 of anything is just x. And cosine of, now this is the sum of two angles, a plus b. Cosine of a plus b is cos a cos b minus sine a sine b. So I'm going to write that out, try and write it out here. Cosine of cosine to the minus 1, 2 over root 5, cosine n pi over 3, minus sine of this angle here, a, which is cosine to the minus 1, 2 over root 5, times sine, times sine of n pi over 3. And this equals, well, let me get a little space here. Let's look at this angle we've got here. This angle cosine to the minus 1, the angle theta, whose cosine to it is 2 over root 5. And I think in the earlier part of the problem we drew this diagram so that other side had to be 1 by Pythagoras because that's a right angle, which means that the sine of theta is equal to 1 over root 5. And that's the same as sine of cosine to the minus 1 of 2 over root 5. All of that's just equal to 1 over root 5. So this equation here at least becomes a little bit simpler. The cosine to the cosine minus 1 just becomes 2 over root 5. And then we've got cos n pi over 3 minus 1 over root 5 times sine of n pi over 3. So I need to hurry here. There are three solutions to this. As a solution, let me just get a little more space here for this. N equals 0, n equals 1, and n equals 2. I'll change to a different color just to finish this off. This one, x is equal to, now if n is 0, that's sine of 0, so that whole term is 0, and cos of 0 is 1, so we just get 2 over root 5, which is the one solution we knew we had to begin with. If n is equal to 1, x is equal to 2 over root 5 cos of pi over 3, which is times a half, minus 1 over root 5 sine pi over 3, that's sine of 60, which is root 3 over 2. And if n is equal to 2, x is equal to 2 over root 5 sine 2 pi over 3, that's 120 degrees, which is, what will that be? That will be minus a half. Minus 1 over root 5 sine of 120 degrees, which is also root 3 over 2. And this is equal to minus 1 over root 5 minus 1 over root 5 root 3 over 2. Okay, I'm going to stop there so we don't run out of presentation time, and I'll finish the last part in an extra bit of presentation. Thank you very much for now, and we'll join again in a moment.